So the two most common measures of center are the mean and the median. Mode is not a measure of center. The minimum plus the max divided by 2 is not a measure of center either. While the mean and the median both attempt to communicate the center of a graph or of a data set, they tell us different information. The median is the value that splits an ordered data set in half. If the number of values is odd, then the median is the middle number in the data set when you put the numbers in order from least to greatest. So we have 5 numbers here. The median is the middle number. If you have an even number of values in your data set, the median is the average of the 2 middle numbers. So here we have 6 numbers. We're going to take the 2 middle numbers, 2 and 3, and average them. Add them up, divide by 2. That's our median. So if you have an even number of values in your data set, your median may not actually be a value in your data set. The median is the midpoint of the data, so 50% of the values are below the median, 50% of the values are above the median. The median is also the 50th percentile. A percentile is the percentage of data that is below a certain point. So the 50th percentile means 50% of the data is below the median. The mean, this is a weird math notation, which we're going to have to get used to seeing. But what it means is add up all of the numbers and then divide by the number of numbers you have. So, right, n is the number of values in your data set. This is the Greek letter sigma, which means sum. It means add them all up. X is going to be a value in your data set. I indicates the number, each individual value. So this means this. The sum of xi, usually it would also have, it would also say for I equals 1 to n, typically. Meaning that for every value in your data set, from the first one to the nth one, you would add them all up. So add up all the numbers in your data set and divide them by the number of numbers that you have. This is a somewhat unnecessarily complicated way of indicating that, but it's good notation for you to get used to seeing. We will do more with sum notation in other sections. And our symbol for the mean of a set of numbers is x bar. It is pronounced x bar. So each of these numbers, x1, x2, xn, represents the n observed values. The mean on a graph is the center of mass or the balancing point. The population mean is also computed the same way. Mu is going to be your population mean. This is the Greek letter mu. Usually we cannot calculate mu because population data are rarely available. If we knew the population mean, we wouldn't be taking a sample and finding the sample mean. Usually our purpose in taking a sample is to approximate the population mean. Which measure of center is going to be more sensitive to outliers? Why? It's going to be the mean. The mean is more sensitive to outliers because an extreme value can have a big effect on the sum and less on the mean. Consider this set of numbers. Okay, so here's a set of numbers. The mean is going to be, right, 1 plus 2 plus 3 plus 6 over 4, which is going to be 3. The median is going to be 2 plus 3 over 2, which is 2.5. The mean and the median are very similar here. If I take this set of numbers, right, now the mean is 1 plus 2 plus 3 plus 98 over 4, which is going to be 26, and the median is still 2.5. So, outlier. The outlier changed the mean a lot and did not change the median at all. So in a skewed graph, the mean follows the tail, or the mean follows the skew. If I have a distribution here that is skewed to the right, your median is going to be closer to the bulk of the data, and the mean is going to be pulled in the center of this, in the direction of the skew. If the distribution is symmetric, the center is often defined as the mean, where the mean and the median are usually the same. In a symmetric distribution, the mean and the median are often the same point. Sometimes they're the mode as well, although you could have bimodal data that look like this, wherein the mean and the median are the same but not the mode. If the distribution is skewed or has outliers, the center is going to be, we are going to use the median as the center. Because in skewed data, the mean is pulled in the direction of the skew, and so therefore the mean is no longer a reliable source of center. So we would prefer to use the median for skewed data. Which is most likely true for the distribution of percentage of time actually spent taking notes in class versus on Facebook, Twitter, etc. So here we have data that are skewed left. So our median is going to be here-ish, probably. And our mean is going to be pulled down. These are just approximations. I don't actually know what the mean and median are, but when you look at enough skewed data, you can sort of eyeball it. My median might be a little bit high, whatever. Right? So the mean is going to be less than the median. So the tail pulls the mean down in the direction of the skew. And here they tell us, okay, so yeah, your median is 80, your mean is 76. Here we have income trends over time. So here is the mean in 2017 dollars, and here's the median in 2017 dollars. And we can see that the mean is consistently greater than the median. But look at the gap. The gap between the mean and the median is widening. So what does that tell us about the distribution of income over time? What it's telling us is that the distribution is getting more skewed right. We are having more and more extreme outliers. Our outliers are getting more extreme and are pulling the mean farther up. Whereas the median not increasing very much, the mean increasing more sharply over time. For boys is 22 minutes and for girls it's 25 minutes. Is this a big difference? Say one girl has a 35-minute commute time to school. Is she far from the mean or close to the mean? In order to answer these questions, we need a measure of spread about the mean. The range is not sufficient because it tells us nothing about how the data is distributed within the range. All right, the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And 1, 3, 5, 5, 5, 5, 5, 5, 7, and 10. These sets of numbers have the same range. They all go from 1 to 10, so they all have a range of 9. They both have a range of 9. But they're going to have different standard deviations. This set of data is more spread out. This set of data is clustered around the mean, which is going to be about 5.5. So we need, in order to measure how spread out the data are, we use the standard deviation. The standard deviation is the measure of average spread around the mean. If the standard deviation for girls' commute times is 3 minutes, then 35 minutes is more than 3 standard deviations away from the mean, which is really big. If the standard deviation is 10 minutes, then 35 minutes is only 1 standard deviation away from the mean, which is not that big. We don't use variance very much. It's mostly going to be the first step on the way to calculating the standard deviation. Variance is the average squared deviation from the mean, and it is the standard deviation squared. So, standard deviation equals the square root of the variance. And so I told you the sum notation was going to come back. So s squared here, this is the variance. And it doesn't even have its own symbol. It's just s, which is the standard deviation, squared is the variance. And we take all of the numbers from 1 to whatever number we have, and we subtract the mean. So this xi is each number in our data set. X bar is the mean. So we take each number, we subtract the mean, we square it. We do this for all the numbers and we add them all up, and then we divide by n minus 1. So for this hours of sleep per night, the sample mean was 6.71. Wow, 671 hours of sleep, if only. 6.71 hours, and the sample size was 217. So for every number here in this data set, we would subtract 6.71 and then square that difference. Do that for all these numbers, add them all up, and then divide by 216. If you're thinking that this sounds like an obnoxious amount of work, you are correct. We will practice doing the standard deviation by hand with some small data sets, just because it is good for you to understand how it's calculated and how changing certain numbers affects the standard deviation. But I'll also show you how to do it on the calculator. It's super easy to do on the calculator, which if you've got a sample size of 217, yeah, you're going to do it on the calculator. Otherwise, you will be there literally forever. So let's pick a small data set to do the standard deviation on. I'm going to have these three numbers. Okay? 1, 3, and 5. My mean is 3. 1 plus 3 plus 5 divided by 3. So my standard deviation, or my variance, rather, I'm going to take each of these numbers. So I'm going to start with 1 minus the mean, square it. Take the next number, minus the mean, square it. Take the next number, minus the mean, square it. And then divide by n minus 1. Our n is 3, n minus 1 is 2. So that's going to be negative 2 squared is 4, plus 0 squared is 0, plus 2 squared is 4 over 2. Your standard deviation is 4 here. Or sorry, your variance is 4 here. Your variance is 4, your standard deviation is 2. The square root of the variance. Not too bad to do for this data set, but when you start having more numbers than that, it's a huge pain. Right, so here is the calculation, or part of the calculation, of the standard of the variance calculation for this hours of sleep, right? Each one of these numbers represents a number that was reported in the data set as the number of hours of sleep people get. So 5, 9, 7, whatever. For every number, we subtract 6.71 and we square it. And then we divide by 216. And that gives us a variance of 2.11 hours squared, which is a standard deviation of about 2 hours. Why do we square, right, in our, right, so sum of xi minus x bar squared over n minus 1. Why do we square it here? A couple of different reasons. To get rid of negatives so that the observations are equally distant from the mean are weighted equally. So back to my nice simple data set here, if I didn't square the numbers, then this 1 minus 3 would be a negative 2, and 5 minus 3 would be a positive 2, and they'd cancel each other out. So we want things that are less than the mean to be weighted equally from things that are greater than the mean. We also want larger deviations to be weighted more heavily. So if you've got one outlier, that's going to give you a much larger standard deviation. Not just linearly, but quadratically more. Standard deviation is just the square root of the variance. So we do all the calculation we just did, and then we take the square root of everything. Has the same units as the data. So for the amount of sleep students get per night, our variance was 4.11 hours squared. Standard deviation, you take the square root, and that's going to be 2.03 hours. So some values are farther away than 2 hours from the mean. So the mean was like 6.7, I think, which would be about here, right? So 2 standard deviations would be about that. 1 standard deviation would be about that far. So some are more than 1 standard deviation away. Some are less than 1 standard deviation away. But on average, they're about 2 hours away from the mean. So we can kind of think of the standard deviation as being something like the average distance from the mean. So a set of values that have a small standard deviation are going to be close to the mean on average. And so a set of values that have a larger standard deviation are going to be on average farther away from the mean. That's not a super precise definition, but it's a good way to think about it. So, right, if your data look like this is going to have a small standard deviation. If your data look like this is going to have a large standard deviation, right? If this line is the mean, on average, these data are close to the mean, and these data are spread farther away from the mean. Standard deviation formula has this divide by n minus 1. When we wrote it, we did it as xi minus x bar squared over n minus 1, and then all into the big square root, right? So by multiplying by the 1 over n minus 1 out front, that just means divide by n minus 1. And just a quick note, sometimes I'm going to write it as x bar minus xi squared over n minus 1, just because I can't remember which goes first. And the thing about that squared is it doesn't matter whether you do x bar minus xi or xi minus x bar. I think this first one is the technical correct way to write it, but it doesn't actually matter, so if you see me mixing them up, don't worry about it. So why do we divide by n minus 1 rather than n? The answer is we want the standard deviation, the sample standard deviation, to be an unbiased estimator of sigma, the population standard deviation. So we don't know the population standard deviation usually, because that would require knowing all of the values in the population, and then we wouldn't be doing statistics because we'd already know everything. We're estimating the standard deviation by taking the standard deviation of our data set. We want this to be an unbiased estimator. So we talked a little bit about biased and unbiased estimators when we did the Beyonce activity. But an unbiased estimator is one where if we do this a bunch of times, we take a bunch of samples, on average, we will get something that is close to the true value. Or that is the true value, technically, if we do it an infinite number of times. And if we divide by n instead of n minus 1, the sample standard deviation is not an unbiased estimator of the population. If we divide by n minus 1 instead of n, that just is a small correction that makes the sample mean an unbiased estimator. All right, so make sure you have the formula written down. So find the deviations from the mean, which means take each number and subtract the mean, square all those, add all those up, divide by n minus 1, and then take the square root. Standard deviation interpreted as the average spread about the mean, the average distance from the mean, something like that. Important, standard deviation can never be negative, right? When we square all these values, we make them positive. And then we take the square root, we can't take the square root of a negative, we don't get a negative square root. Your standard deviation can never be negative. Your standard deviation can be 0. When would your standard deviation be 0? Think about it. Your standard deviation would be 0 if, right, so we have inside a square root sum of xi minus x bar squared over n minus 1. The only way that we can get 0 for this is if what's inside the square root is 0. Right? Taking the square root doesn't make a non-zero number 0. it has to be the numerator that's 0. Dividing by something doesn't make it 0. So when we square all of these terms, they become positive, right? So we can never balance out a positive with a negative. So the only way we could get 0 is if every single one of these terms was 0. Which is to say, if xi equals x bar for all xi in the data set. So if I have a data set that's like 4, 4, 4, 4, 4, the standard deviation of that is going to be 0. On average, these data are 0 away from the mean because the mean is 4 and all of the numbers are 4. We can summarize data set with mean and standard deviation, and we will be doing so much work with mean and standard deviation later. But right now we're going to talk about summarizing graphs that are very skewed, because outliers are going to have a big effect on both the mean and the standard deviation. We saw how outliers can have a big effect on the mean, and if you look at this calculation, right, if you've got an xi that's very far away from the mean, you're going to get a large deviation, and then you square it, which makes it larger. So the mean and the standard deviation can be very affected by outliers. Instead, for smaller data sets, we're going to use the 5-number summary. You can also have a calculator calculate the 5-number summary for you. Your 5-number summary is the minimum value, the first quartile, the median, the third quartile, and the max. Values percentile tells you what percent of the data is below that value. So the first quartile, or the 25th percentile, is the first quarter of the data. 25% of the data are less than that. The 50th percentile is the median. Half the data are less than that. The third quartile is the 75th percentile. 75% are less than that. 3/4 of the data. And then the max. Cumulative relative frequency graph shows the percentiles, which is not super useful for us. So when you're finding your 5-number summary, right? So here, the minimum is going to be 0. The max is going to be 4. Your median is halfway between them, is going to be 2. Split your data in half at the median and basically do the process again to find your Q1 and your Q3. So this would be, so halfway, you don't, when we use the 2 here, we don't count the 2, so halfway between these data would be 0.5, and halfway between these data would be 3.5. That would be our Q1 and our Q3. Min, median, max, Q1, Q3. So here, min is 0, max is 5, median is halfway between these, so the median is 2.5. Now we use the 2 and the 3, so out of this half of numbers, what's the middle is 1, and out of this half of numbers, the middle is 4. So you find the middle of each half to find Q1 and Q3. And when you have, so back to this one, when you have an even number of numbers in each half, you average the 2 middle values, just like you do with finding the median. To draw a box plot, you put tick marks at each of the numbers in the 5-number summary. And we connect Q1 to Q3 with a box. And then we draw lines from the min to Q1 and the max to Q3. A box plot just visually depicts the 5-number summary. It does not show how the data are distributed within those quartiles. You could have all of your numbers close to the median, or you could have all your numbers close to Q1. It only shows the distribution within, it only shows the distribution of the 5-number summary. It can show skew, but it's not going to be very precise. They are good for quick comparison, though. Right, so here's the age of Oscar winners for Best Actress and Best Actor. We can see that the Best Actress, right, for the first quartile here is lower than the minimum for Best Actor. So 25% of the Best Actress winners are younger than the youngest Best Actor winner. And so we can see, 75% of the Best Actress winners are below about 40, whereas 50% of the Best Actor winners are below about 42. These dots at the end are outliers. Comparisons. Box plots of the amount of precipitation in inches per month from 1875 to 2017. So we can see that in July and August, we get less precipitation on average. The median is lower, but also the range is lower. Even the maximum amount, this outlier for August, is lower than, say, the median for January. And here's another one. Salaries for 5 sports. So we can see that for the NHL, the salaries are very close together. For the NBA, the salaries are very far apart. I don't know what's going on here. So your salaries are very, very close together, but then you have a lot of outliers. So that's weird. Here's another one. So this is the same thing, but now it's comparing, now we can see the distribution of the data, right? So you can see how this distribution for the NBA is skewed right, because you've got all these people out here, and then you've just got a few people out here. And then the MLS, right? Everybody's way down here, but then you got a few trickling off. So that's, again, really weird. The IQR. We talked about the IQR when we were talking about SOX, right? One of the S's stands for spread. And we said that the IQR, or the standard deviation, are potential measures of spread. The IQR is the distance between Q1 and Q3. It's literally just you subtract Q1 from Q3. And that's the IQR. It's called the interquartile range. It tells us the spread of the middle 50% of the data. It's kind of like the range, but it gives us, it's not as sensitive to outliers. Speaking of outliers, so when we looked at our box plots, I told you that these dots represent outliers. Well, what counts as an outlier? There's actually a specific way that we determine what an outlier is. And one rule of thumb is to be 1.5 IQRs above Q1 or above Q3 or below Q1. And so these are the ones that get the dot. So on the upper end, greater than Q3 plus 1.5 times the IQR. On the lower end, less than Q1 minus 1.5 times the IQR. All right, so if we have a data set where Q1 is 10 and Q3 is 20, the IQR is 20 minus 10, which is 10. 1.5 times the IQR is going to be 15. So anything greater than 35 or less than negative 5, right? This being 20 plus 15, this being 10 minus 15. These would be considered outliers. It's the same thing that I just said. It did. Formatting's borked. But another rule of thumb is that an outlier is more than 2 standard deviations away from the mean, if we know the standard deviation. If we're doing box plots, we're going to use the IQR because we already calculated the quartiles, so finding the IQR is really easy. But if we know the standard deviation, more than 2 standard deviations away from the mean is considered an outlier. Why are outliers important? Help us identify extreme skew in the distribution, identify data collection and entry errors. If on our, numbers of, hours of sleep per night, we had something like 70, that was probably an error. It was probably supposed to be like 7. But noticing that outlier would help us realize that somebody entered something wrong. Provide insight into interesting features of the data. So I was remarking about that the one box plot where you've got everybody with salaries very, very close together, but then you've got a few trickling outliers. So that distribution would be like this. It's very skewed, which is weird. So the modified box plot, same as the box plot, except we use the we do the asterisk or a circle for the outliers. So here's an outlier, here's some outliers, and then our max and our min are the first values that are not an outlier. The first quartile, the median, and the third quartile are still calculated the same. We're going to be doing modified box plots. We want to see the outliers. So, comparing numerical data, does there appear to be a relationship between class year and number of club students are in? Yeah, to some degree, right? These box plots here are looking weird because the median is the same as the first and third quartiles, respectively, right? So how many clubs is a discrete variable. So here you had a whole bunch of people that are in exactly 2 clubs. That entire, from Q1 to the median, all of those numbers are 2s. And here, from the median to Q3, all of those numbers are 3s. Which does give us a smaller IQR, because here the IQR is only 1. Which is why we end up with so many outliers here, because the IQR there is only 1. IQR here is 2, and IQR here is 3. But the minimum here is the same as Q1. You got 25% of your people who are in exactly 1 club. Whereas here you've got at least 1 person, and here you've got at least one person that's in 0 clubs. Describing and comparing distributions, again, we would use socks. So here, marking the outliers shows that, generally speaking, the female Oscar Best Actress winners are younger than the men. Here, it looks like they have they do have a wider range, but these 3 are outliers. They're not evenly distributed from 40 to 80. So, describing distributions, we're going to use socks again. You want to talk about the center. So we want to talk about the shape, the outliers, the center, the context, and the spread. So it's kind of hard to get shape from a box plot. We would talk about how there are 3 outliers here for Best Actress and 1 for Best Actor. The center is going to be the median. So the median age for Best Actress is lower than the median age for Best Actor, about 35 compared to about 42. The spread, right? We would use the IQR as a measure of spread. So here the IQR is about 10. Here the IQR is closer to 15. And our context would be to use the words ages of Oscar-winning Best Actors and Best Actresses from 1975 to 2004. The spread of male actors is larger than that for female actors, even though the overall range of ages for females is larger due to the outliers. Right, so we talked about socks. Shape, approximately symmetric, right skewed or left skewed. Don't ever say that something is symmetric. It's approximately symmetric. The AP test really, really harps on you for that, approximately. Outliers, center is going to be the median or the mean. Context, reference a variable and its units. So, in the case of the actors, it's your median is about 40 years. Units would be years there. And the spread, standard deviation or the IQR. And put descriptions in context. So, overall, male Oscar-winning actors tended to be older than female Oscar-winning actors. So, Oscar-winning actors is the context. The median age for males is greater than the median age for females. So that's our center. The IQR, or spread of the middle 50% of ages, is greater for males, even though the range in ages is greater for females due to the outliers. That's going to be your spread. Alright, so we've got center, spread, context. The distribution of ages for both is right skewed, with the ages of females being slightly more right skewed. So, right skewed in that you've got these outliers on the end, and that you've got just as many people in this little box as you've got in this box. A box plot that is largely symmetric, right? This is largely symmetric, is not as skewed, although you do still have an outlier here. Right, so this one is the recall time for unpleasant things versus pleasant things. Tended to be greater than, for unpleasant things, tended to be greater than for pleasant things. The median, so there's our center, Recall time for unpleasant things is greater than that for pleasant things. The recall time for unpleasant things has a greater IQR as well as a greater range. There's our spread. The distribution of recall times for unpleasant things is more right skewed than for pleasant things because you've got more here as opposed to here. You've got just as many in this chunk of data as you have in this chunk of data. So and you should mention this outlier. That's the one thing that they're missing here. So they didn't mention the outlier. So, comparing distributions, bell-shaped distribution, right? The boxes are the same size. You're going to have tails that are about the same. A left-skewed distribution, but so the tails are not as big as the boxes, right? You've got the same amount of data here. This is 25% of your data, and this is 25% of your data. But this 25% of your data spans a greater range. Compared to the rectangular distribution, where this, and this are all the same size. Left-skewed distribution, right? More of your data is on the left side, or on the right. More of your data is on the right. The right boxes are smaller, so they contain the same amount of data, 25%, but in a smaller span. And then you've got this 25% of data is more spread out. Right skewed is the opposite. This 25% of data on the high end is more spread out. And then a U-shaped distribution where your boxes are bigger than your whiskers, but I don't think we'll see that. Given a box plot, we can't draw the corresponding histogram because we don't know what data look like in between the quartiles. How would sample statistics such as mean, median, standard deviation, and IQR of household income be affected if the largest value was replaced with 10 million? So, all right, this largest value is 1 million. The scale is kind of annoying. You could have just done annual household income in millions and made this go from, made this go from 0 to 1, whatever. Or in hundreds of thousands and made it go from 0 to 10. Anyways, right? So this largest is 1 million. What if it was 10 million? What's going to happen to the mean? Well, the mean is, this distribution is already right skewed. The mean is going to be, I don't know, somewhere in here probably. If we have an outlier now at 10 million, the mean is going to be pulled in the direction of the outlier. So the mean's going to go up. The median, which is going to be like here somewhere, not going to change. Or maybe it'll change. Well, no, actually. If we take something bigger than, if we replace this value, we're not adding a value. If we replace this value, we just move this to 10 million, the mean's not going to change at all. We take a value that is greater than the median and we make it bigger. Median's not going to change at all. Standard deviation is going to change. Standard deviation is also going to go up. Your data are more spread out now. On average, they're farther away from the mean. IQR, your quartiles, Q1 is going to be here and Q3 is going to be here, something like that. Quartile, your IQR is not going to change at all either. Now, what if we replace this smallest value with 10 million? Your mean, again, going to increase a lot because we have an outlier. Standard deviation going to increase a lot. Your median is going to shift over by 1 value, but it's not going to change a lot. Same thing with your IQR. Your Q1 and Q3 are going to shift over by 1, meaning your IQR will stay basically the same. So these are robust statistics. Robust statistics are ones that do not change very much, are not very sensitive to outliers. So here, in the original data set, the median was 190, and the IQR was 200. If we move the largest value to 10 million, the median and the IQR stay the same. If we move the smallest value to 10 million, the median shifts a little bit, IQR doesn't change. Those are robust, not sensitive to outliers. The mean in the original data set was 245. If we move the largest value to 10 million, it's 309. If we move the smallest value, it's 316. And the standard deviation, originally 226, if we move one of these to 10 million, becomes 853 or 854, right? Because remember that deviations from the mean are squared. So bigger deviations from the mean impact things that are farther away from the mean, impact the standard deviation, not linearly, but quadratically. So median and IQR are robust to skewness and outliers, more than mean and standard deviation. For skewed distributions, it's often more helpful to use the median and the IQR to describe the center and spread. For symmetric distributions, we're going to use the mean and standard deviation. If you want to estimate the typical household income for a student, we would use the median because this is likely to be skewed data. Income is always going to be right skewed. A pair of histograms, or box plots, or dot plots, or stem and leaf plots show the distribution of two groups and are useful for comparing distributions. A scatter plot requires two paired variables and looks at an association between those variables. We would talk about scatter plots a lot in Unit 2 of the AP guidelines, but I am moving that to second semester. But I promise we will come back and do a lot with scatter plots. And that's it. Man, this video was really long.